Good morning, everyone. I'm Pengfei Zhang from Fudan University. It's my great honor to chair this morning session. Our first speaker is Professor Jinsheng Wen from Nanjing University. He will talk about new developments in Kitaev quantum material. Let's welcome.
Okay, thank you for everyone again. And my name is Jinsheng Wen, and I'm from Nanjing University. And I hope it wasn't a mistake to invite me, as I am neither a mathematician nor a theorist. Actually, I'm an experimentalist. So today I will be talking about our recent progress using neutron spectroscopy to study Kitaev quantum magnets, as Professor Zhang just introduced. So in today's talk, I will be telling you two parts. The first part is our study on the spin half alpha ruthenium trichloride, and the second half is about the spin 1 system, sodium nickel bismuth oxide. So first, let me briefly introduce what quantum magnetism is. We know that for conventional magnetic material, they tend to order at low temperatures to lower the energy. For example, depending on the sign of this Heisenberg interaction, you can either have a ferromagnetic order or antiferromagnetic order at low temperatures. However, if you have this kind of structure, for example, a Kagome structure or triangular lattice structure, then for an antiferromagnetic interacting system, it is difficult to for this third spin to be antiparallel to both of these two spins. So in this case, this spin feels strong fluctuation. So this is called geometrical fluctuation, as this is due to the geometrical reason. And in this case, the quantum fluctuation will be very strong. So there can be a new state and new excitation emerging from this kind of strong fluctuation or quantum fluctuation. One typical example is quantum liquid. So Anderson proposed this idea in 1973. So it's just 1 year past a half century. So if you look at this, each of the anti-parallel spin, then they pair together to form a spin singlet. So overall, if you look at this system, it's non-magnetic, because the singlet, you have a total spin of 0. However, this spin actually interact with each other very strongly. So this spin have strong correlation with each other, but they don't have any long-range order. So this is the first character of quantum spin liquid. In addition to this, a spin can have fractional excitations. For example, you can excite this spin singlet to a spin triplet state. Because these two spins, they can have a very long-range entanglement, so you can easily break this bond to have two isolated spin-on. And each of the spin-on actually carries spin half. So the spin is fractionalized. So in this case, you have this kind of fractional excitation, which is spin-on. And these spin-ons can actually move freely in this system without costing any extra energy. So here I summarize two characters of quantum liquid, which one is they don't have any long-range order, and the second one is that they are long-range entangled and can have fractional excitations. So for a quantum liquid, they actually don't break any symmetry, either lattice or spin symmetry. And so it is a third quantum state beyond Landau's framework. And so sometimes you need to use topological theory to describe the phase and the phase transition. And the second important thing about quantum liquid is that Anderson in 1986 proposed that just when high density superconductivity was discovered, Anderson proposed that quantum liquid may be the parent compound for high temperature superconductors. So if you can understand quantum spin liquid, you may able to understand the mechanism of high density superconductivity. And the third thing is that based on the fractional excitations, you may use them to do topological quantum computing. So it is very important to find a real material that is quantum spin liquid. The first is that here I'm just saying there are three important points for quantum liquid. The first one is that it is a third state. This is the second one, and this is the third one. A few years ago, I wrote a brief review summarizing the most studied geometrically fluctuated quantum spin liquid candidates. And for this material, they have this or that problem. So unfortunately, up to now, there has been no single material that has been really confirmed to be a real quantum spin liquid. And among this material with the triangular lattice, ytterbium, magnesium, gallium oxide, was studied most extensively. So this material initially was believed to be a very promising quantum liquid candidate. We actually found another material which is isostructural to ytterbium, magnesium, gallium oxide. We use zinc to replace magnesium. Zinc and magnesium are non-magnetic. Here, the magnetic ion is ytterbium. And we found that the property is very similar to that of ytterbium, magnesium, gallium oxide. And we also found the continuum, which is believed to be the most strongest evidence for quantum liquid. But later we found that actually there are two problems. One is that in this material, the energy scale is pretty low. It's only in the order of 0.1 MeV. And the second is that there is a very strong structural disorder in this material. So we are thinking whether there are any other reason for this kind of continuum. So we collaborate with our theoretical collaborators, and we assume the ground state is a magnetic order state. And then we introduce some structural disorder into the system, so we can actually reproduce theoretically the experimental observation. So these two panels are populations, and these two panels are experiments. So you see that actually they are very similar. So we can also use a structural disorder to reproduce this kind of continuum, which is considered to be a very strong evidence for quantum liquids. So what is a real ground state for this material? We further proceed. we measure the low temperature thermal conductivity, and we don't see any thermal conductivity contributed from the fractional excitation, such as the spinel. And then, so here we can basically exclude that the ground state to be a quantum liquid. So what is the real ground state? We further measure the AC susceptibility, and we found that either for ytterbium zinc, the YZGO, and also for YMGO, ytterbium magnesium gallium oxide, they both have a freezing temperature around 0.1 Kelvin. And this freezing temperature actually has a very strong frequency dependence. So this is a very important characteristic of the spin glass. So we conclude that this material, including ytterbium zinc gallium oxide and ytterbium magnesium gallium oxide, to be a spin glass instead of quantum spin liquid. So it seems that for geometrical frustrated systems, they have this or that problem, and mostly they're coming from the structural disorders. So the question is that whether there is any other rules to realizing quantum spin liquid. The answer is yes. So in 2006, maybe some of you in the audience know that Kitaev proposed a new quantum spin liquid model. By the way, Kitaev also attended this Congress, and he was awarded the Lifetime Award in this Congress. So Kitaev proposed a new quantum spin liquid model on a honeycomb lattice. So different to previous cargol-lattice and triangular lattice. Honeycomb lattice actually doesn't have any kind of geometrical fluctuation if you only consider the first neighbor exchange topping. Then, if it doesn't have geometrical fluctuation, how can the quantum spin liquid state emerge? So the key actually lies in the anisotropic bond-dependent Kitaev interaction. So, for example, if you look at this site, so this site it has three bond anisotropic Kitaev interaction. So, for example, this interaction, these are all Ising type interaction. So this Kitaev interaction will require this spin to align along the y-axis, and this along the z-axis, and this along the x-axis. Then this spin on this side naturally feels a strong frustration. So it can order even at absolute zero temperature, because the frustration is very strong. But this frustration is very different from previous geometric frustration I just introduced. It is on this single side, and it is resulting from the exchange frustration. And one good thing about Kitaev model is that you can solve this simple Hamiltonian, and the ground state is the quantum spin liquid. It is either gapless or gapped, but the ground state is the quantum spin liquid. It's different from the previous triangular lattice and cargol lattice. For those systems, whether the ground state is quantum liquid is still controversial. And if they are quantum liquid, what kind of quantum liquid is also unknown, even theoretically at the moment. This model is very simple and very beautiful, but the problem is that for an exactly solvable model, the dilemma is that often it is unrealistic, and this is also the case for Kitaev model. The problem actually lies in the Kitaev interaction because for a spin system, it is difficult to have this kind of bond-anisotropic Kitaev interaction because the structure is isotropic along these different bonds. So it is unrealistic to have this kind of anisotropic Kitaev interaction, and not mentioning the Kitaev quantum spin liquid. One solution to this problem is you can introduce spin orbital coupling. For example, for 4D or 5D systems, you can introduce a spin orbital coupling. It can further split the T2D band into effective spin 1/2 system. And then this spin 1/2 is actually entanglement of the orbital and spin degree of freedoms. And here, the orbital is d orbital. We know that d orbital is very anisotropic in space. In space. So due to the anisotropy of this d orbital, you may be able to realize this kind of Kitaev interaction, bond-dependent Kitaev interaction represented by different colors, and as well as Kitaev quantum spin liquid. And people even propose that it may be realized in this material, sodium iridase. But the reality is that our experimental colleague found that the ground state for this material is actually not a quantum spin liquid. It actually has this kind of long-range order. This is the zigzag order. So it is not a quantum liquid, but zigzag long-range order instead. You see this kind of long-range order, but it doesn't mean that seeing this is trivial. The reason is that theorists further propose that the reason why you don't have Kitaev quantum liquid state is that here the interaction is not pure Kitaev. It still have finite Heisenberg interaction. So you can use this interaction to construct this kind of phase diagram. So if we look at this phase diagram, there is an area which is close to Kitaev quantum liquid. So if you can suppress this Heisenberg interaction, then you have the possibility to realize the Kitaev quantum liquid state. So the best way to see which material have which kind of interaction is to do an inelastic neutron scattering. So here I briefly introduce the neutron scattering. So neutron actually have a spin and spin half, and it has a magnetic moment. So it can interact with the spin as well as the lattice. So it can deliver the information about the structure as well as the spin. And the most important process for us is the inelastic neutron scattering process. By doing inelastic neutron scattering measurement, you can probe the excitation spectrum. So for magnetic scattering, the cross-section is actually can be directly calculated. So by measuring the excitation spectra, you can know what the spin and lattice do. So you can probe phonons, magnons, and also spinons. But for the material I just talked about, sodium iridase, it is very unfriendly to neutron scattering because iridium actually absorbs neutron very strongly. And another thing is that you can't have high quality large single crystals for sodium iodide. In 2006, Yang Kim in University of Toronto proposed another material, alpha-ruthenium trichloride, which is the main player of the talk today. And he proposed that this material can also have this kind of effective spin one-half of the state. And most importantly, they also found that the system has zigzag order at low temperatures. This was done by neutron deflection. And then, as I just mentioned, the zigzag order state is close to the Kitaev quantum liquid state in the phase space. And there are also some inelastic neutron scattering on the powder samples, which also observe that there are some kind of continuum excitations even above the transition temperature. So people tend to believe that this material may be described by this kind of Hamiltonian, including Kitaev interaction and Heisenberg interaction. So they use this kind of KJ model or HK model to describe this system. So you have Heisenberg interaction and you have Kitaev interaction. So again, the best way to approach this problem is that you have to do inelastic neutron scattering measurements on single crystals, because for powder samples, it doesn't have good momentum resolution. So we managed to get a lot of alpha-ruthenium trichloride single crystals, because for neutron scattering, the scattering cross-section is very small. So you have to have a lot of single crystals. So we managed to get these crystals. We co-align like 1.5 gram single crystals, and then we obtain the single crystal spectra for this material. So this is in the momentum space, and this is the dispersion. So because this material is magnetically ordered at low temperatures, you have this kind of spin wave excitation. It has a gap of about 2 MeV, and the band top is about 7.5 MeV. And then the spectral weight is mostly concentrated around the endpoint, which is consistent with the antiferromagnetic order. And so the next thing is we need to analyze the spectra. So this will require us to get an effective model. So as I told before, people believe that for this material, it should be described by the KJ model or HK model, which is Heisenberg term plus Kitaev term. However, our theoretical collaborator told us that here, the Heisenberg interaction J is at least one order of magnitude smaller than the other two interactions, which is the Kitaev interaction and gamma. Gamma is the off-diagonal interaction. It doesn't have much physical meaning. It's just the diagonal terms in the 3 by 3 times 3 matrix. So then to describe this material, to simplify our discussion, we actually use a new effective model, which is this K gamma model without J. So then we use this model to describe alpha-ruthenium trichloride. So this is the calculation, and this is the experiment. And again, this is the calculation, and this is the experimental result. And you see that actually they fit with each other pretty well. And finally, we found that actually it has a very large Kitaev interaction of about minus 6.8 MeV. which means that the Kitaev interaction is ferromagnetic. And this is very close to the theoretical values without fine-tuning. So it is very good that we in this material we find that the Kitaev interaction, the anisotropic Kitaev interaction, can really be achieved in real material with the aid of spin orbital coupling. So this is good, but it's not still not good enough. The reason is that, as I told earlier, this material, the ground state, is zigzag order state. It is not a quantum liquid state. However, we found that the magnetic order is quite fragile. The magnetic ordering temperature is only about 7.5 Kelvin. So we apply in-plane magnetic field, and then you can either measure the specific heat and then also the magnetization. We found that at zero field, there is a very sharp peak representing the magnetic ordering temperature. And then if you apply a 7.5 Tesla field, the magnetic order transition is completely suppressed. You can see from here or from here. And then you enter a magnetic disorder state. So is the magnetic disorder state a quantum liquid state we are looking for? To answer this question, we further collaborate with Wei Qiangyu at the University of China, and also Fu Shiyan Li at Fudan University. And Wei Qiang did the low temperature NMR measurements, and Shiyan did low temperature thermal conductivity measurements. And they both found that there is a quantum critical point around 7.5 Tesla, and then they also get some evidence showing that the system may be developed quantum liquid near this critical point. So to further confirm these conclusions, we did a series of neutron scattering measurements. And here I just summarize our key results. So at a low field, the system is actually a gapped zigzag order state, and at high field, because if you apply a strong enough field, you will eventually polarize the system. But here the field is not strong enough, so you only partially polarize the system. At the intermediate range, you have this kind of a gap, this quantum liquid state. We have this conclusion. We draw this conclusion by looking at this spectrum. So now let me summarize our results on alpha ruthenium trifluoride. So now the most the things we are sure about alpha ruthenium trifluoride is that the material is better described by this model, K gamma model, instead of KJ model or HK model. And then you indeed can have a very large ferromagnetic Kitaev interaction in a real material. And then we can also use magnetic field to induce a quantum liquid state. So all these are on the effective one-half systems. So next, let me spend some time trying to introduce our work on another S equals to 1 system, sodium nickel bismuth oxide. So we know that the Kitaev model was proposed in 2006 for spin-half system. Since then, there are many theoretical proposals proposing that you may also realize similar physics in higher spin system, although it doesn't have exact solution like that for a spin half system. But then you can discuss, you can have this kind of Kitaev interaction, and you can also have gap-based quantum liquid state for S equals to 1 Kitaev model. And people also even propose some material to be the candidate for Kitaev quantum liquid. Because this material is very similar to sodium iridase or ruthenium trifluoride. Because, for example, they also have this kind of edge-shaped octahedral structure, and for this material, they actually have 3D ion. So in principle, they don't have very strong spin-orbital coupling. However, due to the proximity effect of this heavy anion atoms, you can have some kind of fine spin-orbital coupling, and it has effective spin one-half state. And most importantly, they also have zigzag order at low temperatures. So we try this material on sodium nickel bismuth oxide. So we measure the susceptibility, and we found that the magnetic order is very anisotropic, and it has a long-range zigzag order below new temperature of 10 Kelvin. And then the magnetic order is very anisotropic. You can apply an outer plane field. This is along the c-axis, and this is along the AB plane. And you see that along c-axis, the magnetic order is suppressed rapidly, but for the field applied along AB plane, the magnetic order is suppressed more slowly. And most importantly, for the field applied along outer plane, we found that actually there are 3 steps. So to look at this step more carefully, we can do magnetization as a function of field. We can obtain this kind of MH curve, and from this MH curve, we actually found these 3 steps more clearly. So the first step is around the magnetization equal to 0. This is due to the presence of the single ion anisotropy. So you need to overcome this gap to have a finite magnetization. And then finally, you can apply a very strong field above 7 Tesla. Then you can fully polarize the system to have the fully polarized state. And then for the fully polarized state, you have a saturated moment of 2.1 mu b. And then a most important step we observe is this one. So this step is corresponding to 0.7 mu b. So 0.7 divided by 2.1 is exactly 1/3. So we have this kind of 1/3 plateau, and then we can also do some derivative, first derivative to this MH curve, and we found that the plateau enlarges if you decrease the temperature. So this means that this kind of plateau is actually due to quantum reason instead of the thermal reason. So next, we will want to understand what kind of magnetic structure for the material in zero field as well as in the plateau phase in 7 Tesla field. So we found that this is the experiment, and we do some simulations to calculate the structural patterns. And then by comparing the experiment and calculation, we can determine the structure and zero field is this kind of zigzag order state. And so this is relatively simple, but for high field in the plateau phase, the structure is very complicated. So the structural pattern is totally different from that at low field. And so finally, after many tries, we eventually determined this kind of magnetic structure to be the structure at the plateau phase. So we have this kind of structure. We define this site as spin zero. Spin zero means that the spin lies on the epiplane. So it doesn't have a moment along outer plane direction. And then you have this zero up, zero down, up, up. So we also need to enlarge this cell to include the 6 sites. So here, in the fully polarized state, you have 6 up spins. But here in the plateau phase, you have only 2 up spins. So 2 divided by 6 is exactly 1/3. So this actually explains why we have this kind of plateau phase very nicely. So based on these results, we can construct this kind of phase diagram. At low field, we have the long-range zigzag order phase, and at high field, we have the fully polarized state. And in the intermediate fields, we have this 1/3 magnetization plateau phase, and this is resulting partial spin flop of this zigzag order state. So why what's the meaning for this kind of plateau phase? People mostly study this kind of plateau phase in the triangular system or Kagome system, because for triangular system, we know that there is a strong geometrical fluctuation. So you have many kind of degenerated ground state. So then from a classical point of view, all these systems have equal energy. However, if the quantum effect is strong enough, you have to consider the quantum 0-point energy. Then, if which kind of state has the lowest 0-point energy, this state will eventually win. So this mechanism is called order by disorder mechanism. So so you have a strong quantum fluctuation, but this kind of quantum fluctuation will give you an order state. So this sounds weird, but it is actually realized in quite a few triangular systems. And people also propose that very recently, this is a paper just published this year. They also observed this kind of plateau phase in the Kagome system. However, as I said earlier, this system is actually having this kind of honeycomb-lattice. And for honeycomb-lattice, it doesn't have geometrical fluctuation. Of course, you can consider longer range interaction. For example, you can consider J1, J2, J3, and then this kind of combination can give you exchange fluctuation. But this still cannot explain our experimental observations. And since we did a lot of work on alpha-rho trichloride, we are familiar with Kitaev interaction. Kitaev interaction, we know that it can give you this kind of magnetic fluctuation. So then we collaborate with Wei Li from Institute of Theoretical Physics, and he did quite some calculations. And the key finding is that in this material, the third neighbor exchange coupling is comparable to J1. However, J2 is negligible. And only if you include Kitaev interaction can you expand all the experimental observations. So this is the key results from their calculations. They calculate the variational energy. So if you don't have the Kitaev interaction, the three states, which is the zigzag order state, the fully polarized state, and also the red line representing the 1/3 magnetization plateau phase, they all have the same variational energy at this point. If you include a finite Kitaev interaction, you can significantly reduce the energy of this 1/3 magnetization plateau phase and stabilize this kind of fractional magnetization plateau phase. And they also calculate the magnetization as a function of the magnetic field. And this also looks very similar to our experimental observations. So then finally, we conclude that you need to have a finite Kitaev interaction to stabilize this 1/3 magnetization plateau phase. So here, let me briefly summarize our work on sodium nickel bismuth oxide. So we first found that there is a magnetization plateau phase in this honeycomb-lattice, and honeycomb-lattice is without geometrical fluctuation. And also, we attribute the plateau phase to be stabilized by the anisotropic Kitaev interaction. And by doing so, we actually extend the Kitaev physics from spin 1/2 to spin 1 systems. And finally, the most important message I want to deliver is that quantum mechanism is much more than just quantum spin liquids. Because here, actually, the magnetization plateau phase is a magnetically older state. It is not a quantum liquid state. But quantum mechanism also work in this kind of older state. And even for the string supersolid, it is also within the scope of quantum mechanism. Then finally, let me acknowledge my collaborators. So most of this work done by my students, and so these are my group members. And also we have very strong theoretical support from our internal collaborators led by Professor Jinsheng Li, and this is Professor Shunli Yu, and Wei Wang and Dong Yaoyang are Professor Li's former students. And we also collaborated closely with Wei Li at Institute of Theoretical Physics. And we did many neutron scattering measurements, and all these measurements were done worldwide. For example, these spectrometers are located at Germany, and these are located at Australia, and this is located at Japan. And this is also in Germany. and we also have some funding support from Mott and National Science Foundation of China. So now, finally, let me summarize. So in today's talk, I actually gave you two examples of how we can use neutron spectroscopy to study the Kitaev quantum magnets. So we have two systems. One is a spin-1 and we can also extend the discussion of Kitaev physics to the spin-1 system. So with all this, I would like to thank you all for your attention and welcome your questions if you have any. Thank you very much.
From the right-hand side, it says the quantum spin liquid should be gapless, right? So from this diagram. But
yes.
Yeah, but from the left-hand side,
we didn't plug it to the zero energy. Actually, it has this kind of. So let me spend some time expand this thought. So this is the most important plot why we draw this kind of conclusion. Because magnetic field equals to 7.5 Tesla, it is a magnetic disorder. So it doesn't have any spin wave originating from M point. It only have this kind of continuous spectra at the gamma point. And this spectra actually extended to zero energy. Yes.
See. Okay, maybe I ask a second question on second part. So I'm just curious, for the spin-1 case, if you have a Kitaev model, is that a quantum spin liquid? Just have a Kitaev interaction.
Well, as I said earlier, it is not exactly solvable, right?
Yeah.
For spin-1. But people have calculated first. They proposed that due to the spin orbital coupling, you can have this kind of anisotropic Kitaev interaction. And they also calculate that the energy for Kitaev quantum liquid, and they found that the energy can also be the lowest among the phase space. So theoretically, they conclude that you can also, in principle, realize the gapless quantum liquid state for S equal to 1.
I see. Thank you. Okay, if you do not have more questions, let's thank speaker again.
Okay, thank you very much.